Physics, and I'm very glad to introduce my old friend, really old friend. I've known Professor Tao Han since, I don't know, almost 30 years. Professor Han is a well-renowned collider theorist. He did his under and master degree at Nankai University in China and finished his PhD at Wisconsin-Madison in 1990. And he spent 3 years at Fermilab as a postdoc, and then went to UC Davis as assistant professor, and moving back to Madison in 1997, becoming full professor there in 2001. And in 2011, he moved to Pittsburgh, his current position, where Pittsburgh created the PIT PAC. PAC stands for Particle Astro Cosmology Center. And I was just joking with him. He's been sitting on many committees, including deciding other people's prizes. He became an APS fellow in 2003 and received the Frontier Fellowship from Fermilab in 2004. And since his Chinese background, he received outstanding research from NSF of China in the early 2000s. In the last 3 years, he's been a 1,000 talent professor at Tsinghua University in Beijing. So there are many things more to talk about. I think I'll now let him speak about the physics. So, Tao, it's your floor.
All right. Thank you very much, George. It's really a great pleasure to be here. And it's really an honor to have this the colloquium together with Yifang. And it's a wonderful talk for the great vision. And it's really exciting, in particular for the young generation, that we have so much to move forward and to look forward as well. However, it gives me a great difficulty to follow some great vision. But I would just try to fill in some of the physics arguments so that we can share some details to build up upon this excitement. So, as George said, currently I'm at the University of Pittsburgh, and this is a very beautiful campus that reminds George something too, and he did his postdoc work some time ago there as well. And of course, this is our beautiful campus here. So, I want to discuss the most exciting issue in the recent years in particle physics. In fact, I would say it's not only in particle physics, in the overall science, it's such a major discovery for so many years hard work, and also gives us the vision for the future, what we can do. There's quite some overlap in terms of physics topics from Yifang's talk, but I will try to give some filled-in details, in particular to our students and also some of the colleagues from other disciplines. So, of course, everybody knows that 2013 was a year that the Nobel Prize was awarded to particle physics, and the quotation is that for the theoretical discovery, but it's based on the experimental verification, but after CMS collaborations at CERN Large Hadron Collider. So that is, for these two plots, you see the discovery plots when was first announced in 2012. So this is a diphoton mass, EMART mass distribution over a very large mass range, and with a continuum standard model expectation or background. If you detect photons, there are many photons, but it's kind of what we call it a background. However, on top of the background, there's such a very feeble signal. So this is very similar to the detection of your TV signal or radio signal. You tune your frequency, you tune your the wavelength, and you find some sound above your continuum background. That's your signal. You listen to a music from radio or something. So these signals are big enough to have a 5 sigma standard deviation, which is the standard for particle physics discovery, both by Atlas and CMS collaborations, both published in physical letters here. And this is in the mass range, about 125 GeV region. That is 125 times more massive or more energetic than proton mass. Proton mass is pretty heavy in our normal standard already. It's 1 GeV. Okay, so there's but this particle, the signal here is 125 times more than that. But it translates that into your kind of a radio signal That is about 10 to minus 9 nanometers. Of course, nanoscience is one of the important topics in both scientifically also industrially. But we see that what we have been working on is much shorter, much higher energy, shorter distances. 10 to minus 9, 9 orders of magnitude shorter than the nanoscience. So of course, this the recent update that was took place with the discovery announcement in 2012. But this year, and after some new data taking a new analysis, and this is this summer's report from Atlas CMS collaboration in the combined result. Here is a coupling for this particle to fermions. Fermions referring to spin half, like the electron muon, and this is tau, just a heavy electron here. And here is a coupling for bosons. Bosons is spin integer, like spin 0, spin 1. So now you see this particle couples to both fermions and the bosons separately according to the theory prediction. And this is the 1 and the 1 is the standard model prediction. You can see that both at this level, you reach 5 sigma for individual channels. This is a very strong confirmation for what the property we really expect is. It is a neutral particle because 2 photon. It is a boson because it doesn't have a spin half. It only has spin integers. But it is a spin 0 and a parity even, and a couple to mass because it coupling to different particles is linearly proportional to the muon particle here. The muon, of course, is only a bond so far. The tau was measured, 5 sigma already, and the B quark is getting there, not the complete 5 sigma yet. And WZ, heavy particles, the weak bosons here. So you see, it's not universal. The coupling is proportional to the mass. That's exactly what the standard model prediction for this particle should be. So in all indications so far, they point to this discovery for these new particles. Of course, this made big news. It is really a milestone discovery, and it's a brand new particle, a different class, never seen before because of this particular property. I will comment all the details in the next 30, 40 minutes or so. So of course, it made to the cover page for these physical letters, these two articles I showed you. And of course, it made the science as the science breakthrough of the year, the Higgs boson discovery. And of course, it's far-reaching even to the society. And Fabiola was the spokesperson for the Atlas experiment, and she made it to the number 5 running up for the Time magazine. So this is highly non-trivial. This is 50 years of theoretical hard work, everything from beginning of this proposal, the Higgs proposal. In 25 long years for the experimental hard work, including the detector design, machine design, and the build out, and finally to take the data and analyze and find this particle. It's really quite unusual. And also, I should congratulate to our colleagues here in Taiwan who have a very large involvement, significant contribution to this particle discovery as well. So let's go back to see what is happening, what we are talking about. We all know that we have different forces acting on us. Okay, so here is gravity to drag the apples and also drag over our satellites. It's the same universal gravity coupling. The gravitational coupling, as we know, is long range. It dies out like a 1 over r squared from Newton's law, gradually, but it tends to infinity. It's like that. Electromagnetic interactions we also know. Static situation for the static interaction is also Coulomb interaction with the same form. It's proportional not to the mass, but proportional to the charge. It's just the sources. Okay. So these are proportional to charge and some coupling constant in front. We call that the fine structure constant. It's also same nature. It's a long range. It dies out like 1 over squared and it goes further and further to infinity. That's the two forces we know. However, the weak and the strong forces are nuclear forces. We usually don't appreciate that around us. Only when you reach the subatomic level, you see that. That is the reason we don't see that. The reason is that the interaction is short range. The short range means there is a kind of a suppression than the 1 over r. There's a significant suppression if you move to a longer distance. Okay. So I deliberately write this into a dimensionless quantity with m to indicate, in fact, it tells you something about a kind of a mass dimension. There's a mass dimension that is basically the so-called the propagator, the mediator, the force mediator. Just like you pass me a basketball, the basketball is a mediator to transmit the force between us. And the heavier the mediator is, the shorter the distance will be, they drop. But the lighter this mediator is, the longer the propagation it will be. So this mask here indicates how long, how short the nuclear force will be. So that was that all these four forces around us would be just like this, around all our world. However, given the new discovery, we have a deeper and more understanding about nature. So for those who have learned something about field theory, just for the sake of generality, I can write this simple equation as action. And this simple equation includes all the forces and all the discovery reasoning we made. Here's gravity, okay, of course in the form of a general relativity. And here is the field, like the electromagnetic field and the strong and weak forces. And here are the Dirac equations for the matter field, formulas, electrons, so on and so forth. And here include the new discovery of the scalar field, which is the background. It's our vacuum background, it's the Higgs field. So in principle, this is everything. And if you integrate over available paths, so this is the so-called path integral formula to give you the possible quantum description. So in principle, this single line includes everything we know. But in reality, we have to get into the details. Let's get into the details to see what our current understanding is. We know that electromagnetism is the most powerful, most successful theory, not only in theory, but also in practice. In long distance, we know this is simply the electromagnetic field propagation, and this gives you the modal part of the Maxwell equation. Okay? So here, this is the tensor form in terms of the field tensor and in terms of the field wave function here. And here it's called a covariant derivative to keep this particular symmetry. We call this a gauge symmetry. So at the low energies, which means long distances, in long distances, Maxwell equations give you the correct description, and it's a purely vector-like interaction following this gauge symmetry that we all know even from the classical ELA. However, at high energies, and then we have to make the quantum mechanical, this is called quantum QED, quantum electrodynamics. So quantum electrodynamics is a quantum version of this one, and it's renormalizable, and most accurate calculations can be quite predictable, and this is the most accurate theory, not only in theory. In fact, it's most accurate theory in the whole science. The accuracy to compare with the theoretical prediction and experiments, such as this the so-called magnetic, the anomalous magnetic measurement for the electron, is accurate to 10 to the 13 digits. So here the comparison between theory and experiments. This is one part of the trillion accuracy. So this theory is the most successful theory in the whole science. However, if you continue on to go to a higher energies, and this quantum electron dynamics becomes kind of sick. The reason is due to this screening effect. Think about a charge at the interaction. Because of vacuum fluctuation, this charge always attract, because of vacuum quantum mechanical effect, attract some other negative charges. So therefore, if you probe this charge from distance, okay, you probe the charge because of screening is less than the reality. The deeper and deeper level you probe this, deeper and deeper you go, the more and more accurate you're probing this charge, but it becomes bigger and bigger. So therefore, in extremely high energy asymptotically, this coupling becomes very, very large. So this is the evolution according to your distances or energies. You can see that at very, very large energies, this term here makes this coupling bigger and bigger because of negative sign here. So therefore, this theory stops being accurate, and this theory becomes sick. So this quantum electrodynamic could not be applied to arbitrarily high energy, although it can be applied to extremely high energy, but not forever. Asymptotically, this theory may be replaced by something else to have a better description. So that is one lesson we want to comment on. Let's look at some vectors. So therefore, we call it UV, ultraviolet energy. This theory is not complete in terms of UV sense. So it's invalid at some point. Let's look at strong force. The strong force, we have very similar formulas. We call it quantum chromodynamics. So it's very similar to the QED. And here, this is the propagating field. But the interaction has more than one charge. Okay, the three charges we call colors. So this interaction here is called another Billian theory. Is at the special unitary but with the three charges here. So then, instead of a normal F mu nu, it has an index A to label the different generators, different propagators, 8 of them, according to this theory. So therefore, you can see that this interaction is not only among the fermions particles, but even among themselves, because of this nature of this non-abelian, rather than the simple U1. So because of that, it is an anti-screening effect. That means if you probe this one closer and closer, because of the anti-screening effect, you probe the more and more accurate charge, and rather than the further away, the charge becomes bigger. The charge becomes bigger and bigger. So if you calculate the evolution, you find a coupling constant at a shorter and shorter distance, a larger and larger energy becomes smaller and smaller. So this is called asymptotically free. That means that when you go to ultraviolet high energy, the interactions becomes almost zero. Essentially, it dies out. So this, of course, is famous. This is the Nobel Prize winning discovery. That's exactly Dave Gross the Nobel Prize because of the discovery of this asymptotic freedom. So this is extremely important. Only because of this consequence, we have the highly predictable theory at high energies, unlike a QED. That gave us the confidence, gave us the possibility to even think about high energy physics. At higher energies, you have the prediction. You know, you can understand nature better because of this the asymptotically free theory. It also gave us the possibility to understand early universe. At early universe, the temperature is extremely high, energy is extremely high. At that region, this strong interaction becomes very, very weak. We're able to predict, calculate, and compare with experiments. Otherwise, we would be out of our capacity to do the comparison. So therefore, the asymptotic freedom like this, the coupling constant becomes smaller, as long as this is a positive sign. If this is a positive sign, that means number for particles, number for quarks, number of flavors, we call that, is less than 16 also. In fact, in our nature, so far we only found 6 quarks. Right? So we are pretty safe to see this. This plot is not only a theoretical prediction for the line. All these dots are real measurements. The real measurements have verified this feature. So we understand the strong interaction very well. Of course, it's challenging from other angle. At the longer distances, at the lower energies, as we said, the interaction becomes strong. And at a distance at 10 to the Fermi level, or femtometers, okay, 1 Fermi, the femtometer, 10 to the minus 13 centimeters. In that region or longer distance than that, this interaction becomes large. That's a strong nuclear force. So therefore, strongly interacting quarks with interacting very strongly, they condensate into a color singlet, non-charged particles, such as pions, protons, neutrons. That's what you and I are made of. We are made of colorless particles, protons, neutrons, and so on and so forth. So that is why the long distance behavior is almost like these hadrons. We call it hadrons, rather than the quarks and gluons, rather than this theory. This theory is modified to a more appropriate description in strong interactions. So that's the strong force. Now, the short range force is the strong force is dynamically generated by this condensation type of things. So the suppression factor, the short distance, is cut off by this the typical mass. The typical mass, the condensation scale, the pion mass. Okay. So that is the reason. Now let's look at the weak force. Weak force turned out to be the richest in terms of physics. Weak force comes from the early discovery even in the 18th. Okay, in the 18th, by the end of 18th, we learned how this 1980, 18th century. So that was what you find for this beta decay here. But that beta decay tells you a charge transition from a neutron to a proton, the change charge. And here, the final state is an electron and a missing neutral particle. It's not change charge. It's different. It's different from electromagnetic because it's only transmitted into no charge changing. And it's different from gravity. It's a new force from a new charge. So we call it charge current. Fermi was the first one to propose interaction. And learning from the successful example from ENM, and he constructed the weak interaction by one current, very similar to the electromagnetic current, but it's a charge current. He constructed another current from other side, so the propagation in between will be parameterized by a dimensionful quantity called the Fermi constant. The dimensionality of this Fermi constant immediately tells you there is a scale. There's an energy scale associated with that. That scale is immediately translated into the distance. So that is 10 to the minus 18 centimeters. Sorry, 10 to the minus 18 meters. Okay. So you can see that that is the reason that there's a very short range weak force because a very, very heavy scale, which of course is given by the parameter here. The parameter is related to this propagating mass. So that is the situation. But how to describe this in a more complete theory beyond this simple parameterization of Fermi? So that was the beginning of the so-called standard model. So the beginning of the standard model was based on this so-called Yang-Mills theory. It's SU2 because you need three particles, the W plus W minus and neutral one. In this theory, you have the charge currents, you have another weak interaction neutral current. So that is one. So this is the theory. Glashow was the first one to put this into the form. However, you see this theory is once again a massless. Okay. There's no mass terms for this gauge bosons because the local gauge symmetry prevents the existence of the mass. So the photon is massless. That theory is okay. You can see that. And gluons are massless. That's also okay. But gluon generated dynamic mass is a different story. But here we know it has to be a massive because of scale here. But how to incorporate this mass into your theoretical construction? Because this mass term does not respect the gauge transformation. It doesn't come back. So the fundamental symmetry to govern your interactions would be inconsistent with our mass term. So what happens here? So they're very, very difficult. So this is Pauli's rejection to Yang-Mills theory. Pauli is that some of you may have heard this story that when Frank Young was giving this talk in Princeton, and Pauli stood up and did not let it go. Okay, so it was even longer story because of time. I won't want to get into that. But that was a rejection. How we can generate masses? Situation becomes even worse when you think about the fermions. When you think electron, electron is massive. We know electron mass have MeV. We know that. But our heroes, Professor TDB and Xin Yang, constructed this argument to say that the weak interaction may not respect the left-right symmetry, the parity. If that is the case, the left interaction and the right-hand interaction will be different because it's not symmetric. If you follow that rule, this is the construction of the standard model. All these left-handed interactions form a doublet. This is exactly what beta decay tells you. We are forced to accept this formalism because beta decay tells you electron transition to neutrino from this doublet. But this is the only left-handed only. Was of course Professor Wu Jianxing's experimental verification. The weak interaction is only left-handed only. Right-handed would not have this the transition, would not have this parent. Right-handed is a singlet. It means it doesn't have the weak charge. Following this, you will not be able to write down the mass. Fermion mass is also forbidden by the gauge symmetry. So here is the fermion mass, electron times electron as itself. There's a dimensionality in front of that, electron mass. If you decompose into left-handed and right-handed components to match interaction, you have a mixture of right-handed and left-handed. They don't form the invariance. The left-handed one is a two-dimensional vector. Just like two vectors, one is two-dimensional, one vector is one-dimensional, they don't product. Product would not be invariant. You could not write down the mass term. So this time mass term also forbidden by interaction. So electric weak theory, gauge theory, must be massless to be consistent with the interaction. But we know that's not true. Weak interaction in the short range, electron has mass. What happens? Then they came up with this brilliant idea. The symmetry probably is still true in your theory, but the ground state, quantum mechanical ground state, may not be respecting the same symmetry. So this is called symmetry is broken, but not as explicitly, but spontaneous. The spontaneous symmetry breaking is the idea that Lagrangian of the system may still display the symmetry. But the ground state, that is our life. We live in the ground state. When you solve a quantum mechanical problem, you found the ground state first. Once you found the ground state, you would do the perturbation around the ground state and see what happens. That's what our real life happens. But the ground state may not necessarily respect that. And this is quite a common example. Let's see this. For example, ferromagnetism would behave like that. At the high temperatures, the domains would randomize itself. If you look at the magnetization, it's basically in the macroscopic level, it's zero. It's completely randomized. But if you keep this to a lower and lower temperature, and until you reach some critical temperature, and all these domains would line up towards one direction, and that is a new ground state. That is the lowest energy state at that particular situation. Then all these domains will line up towards one direction. The original three-dimensional rotational symmetry becomes two-dimensional. And this is the reduction of the symmetry. The symmetry is reduced from the three-dimensional rotation to a two-dimensional rotation. This is a spontaneous symmetry breaking. Because the theory hasn't changed. Maxwell equations behave exactly the same as before with respect to same symmetry, but this particular ground state, particular physics condition is different. It doesn't respect same symmetry. That happens all the time. In fact, the low temperature superconductivity behaves very similar. I will come back to this point. It is a symmetry breaking. But this symmetry breaking process is an interesting new concept, spontaneous symmetry breaking. This is very profound, but the phenomenon is quite common. Maybe we can make use of this symmetry breaking to connect with the mass. However, there's a famous theorem, mathematical theorem, which is very applicable to physics. It's Boson. It's called got Nobel Prize in connection with this the argument that way. That is a mathematical theorem to say that if there's a continuous symmetry of the system, but if that symmetry is spontaneously broken with respect to the ground state, then because of the breaking, there will appear massless degree of freedom, and they call it non-Boson boson. But as Pauli said, there are no any other massless particles besides photon in the gluon maybe. But if this is true, the SU2 theory I mentioned there would have this massless Boson boson. Except the boson, no other massless particles, long-range forces have been seen in our nature. So this theorem basically tells you the spontaneous symmetry breaking idea is in trouble to apply. So the spontaneous symmetry breaking here is a brilliant idea to make the connection between symmetry and non-symmetry. It's quite common in our real world, but is basically forbidden to apply because of this non-observation, non-Boson theorem. It may be a showstopper for us to continue. This is where all this magic comes. So this is called Higgs mechanism. That is in 1964, and Peter Higgs and other contemporaries realized if this continuum symmetry is a local gauge symmetry, exactly like we described. If that is the case, the spontaneous symmetry breaking here will generate the boson bosons, but these boson bosons will combine with the massless gauge boson to acquire mass for this thing. And basically, the massless theory will absorb the boson boson into a massive mode. But that is a major observation, of course. So that was the first paper in the 60s by Angler and Broad, and that's Angler shared the Nobel Prize with Peter Higgs, and Broad unfortunately passed away just a year before. But here Angler Broad is here. Professor Broad is here, and they a year before they came to the U.S. to receive the Sakharov Prize. Sakharov Prize is the highest theoretical physics prize in the U.S. in the community. It's a parallel to the Panofsky's prize that Yifan received. That was the experimental aspect. So this is the time they came to the U.S. to receive the Sakharov Prize, but Peter Higgs, because of the reason he did not go. But of course, the Nobel Prize he did. Okay. So he did go there to receive. So here was the second paper Peter Higgs sent in, I think it's just a month after. And third paper with the PRL paper, Peter Higgs sent out a month later, and those are the Glarenes and Hagen and Keeble. So here to send in the similar topics 2 months later. Okay. So that was the magic to realize this condition. So this condition here is that how to generate this gauge boson mass to absorb these boson bosons. Since I've seen so many students here, we have to go through some calculations, right? So that otherwise we'll feel bored. So we'll just go through some real calculations. Here is really the original example. Here is exactly the original example that Peter Higgs gave. He was looking at the electromagnetism we are very familiar with. Simply your QED. So your Maxwell equations here is. But he introduced this the new scalar field. Okay. The new scalar here is complex field with a real component and the imaginary